You there? Now, is the slide visible?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay. So I'm starting. Okay. Otherwise, it will be too late. What can I do? So, in my last class, I have started with deadlock. We discussed what is deadlock, the general aspect of deadlock, and how deadlock is in the computer system. When a deadlock occurs, you have a set of processes and a set of resource. This set of processes are concurrent in nature. They exist in the system at the same time, so they may have a different resource requirement during their executions. So we discussed when a deadlock can happen. So we discussed 4 characteristics to be in the deadlock. It was mutual exclusion, hold and wait, no preemption, and circular wait. If all the 4 conditions are satisfied simultaneously, then there is a possibility of deadlock. Okay, if all the 4 conditions satisfied simultaneously, then we will say it is a deadlock situation. Then we discussed the formal representation of deadlock using a graph. Graph is nothing but it is a G equal to VE, where V is a set of vertices and E is a set of edges. Here V can be of 2 types, either it can be resource vertex or process vertex. Similarly, edge can be of 2 types, it can be request edge or it can be an assignment edge. With this graph, we can represent the set of processes, set of resources, and their execution state. Once we have the resource allocation graph, by analyzing the resource allocation graph, we can say whether a deadlock exists or not. So first thing that we need to check whether there exists a cycle in the graph or not. If there exists a cycle, then the next thing is whether there exists one single resource for each single instance of each resource, then there is a possibility of deadlock. If there is more than one resource, then there may be a deadlock, there may not be deadlock. For example, this is a situation of deadlock where a cycle exists and one process is waiting for a resource that is held by another process. So in this way, it forms a cycle. We discussed resource allocation graph with cycle but no deadlock. Resource allocation graph but no deadlock. It is not deadlock because though there exists a cycle, because the reason is the resource R1 has more than one instance of the resource. Similarly, resource R2 has more than one instance of the same resource. So there won't be a deadlock. So in summary, we discussed if graph contains no cycle, no deadlock. First, if graph contains a cycle and if only one instance per resource type, then deadlock. If several instances per resource type, then there can be deadlock, there may not be deadlock. You cannot say with a guarantee that there will be a deadlock. So far we discussed the deadlock situation, the reason for deadlock, what are the characteristics to be deadlock, how to represent deadlock situation in formal mathematics. Now today we will be discussing methods for handling deadlock. Okay, so ensure that the system will never enter a deadlock. So you have to ensure that the system will never enter a deadlock. Or the second can be allow the system to be in the deadlock. Once it is in the deadlock, then we will try to recover from it. That means without taking any kind of prevention mechanism, allow the system to be in the deadlock. If there is a deadlock, then we will take care of it. The third option is ignore the problem and pretend that deadlock never occur in the system. Use most of the operating system like Unix. And if it happens, maybe you can go for restarting the system. So these are some of the way in general, in a more abstract way, to handle deadlock. Now in a more specific, the first approach is deadlock prevention mechanism. So deadlock prevention, deadlock avoidance, and deadlock detection. So first one is deadlock prevention mechanism. Restrain the ways requests can be made. That means we have to make some mechanism with which out of these four conditions, four characteristics, like mutual exclusion, hold and wait, circular wait, and then no preemption, one of the characteristics fails. If one of the characteristics fails, then we will say we can achieve deadlock prevention. So somehow we need to find out the mechanism to not to satisfy one of the characteristics. So for mutual exclusion, this is not possible. So because for mutual exclusion, if it is a shareable resource, then there is no questions of mutual exclusion. But if it is a non-shareable resource, then there must be a mutual exclusion properties. As I told you, there's a fan is a shareable resource. So for fan, you don't need to go for mutual exclusion properties. But it's a LAN port. If it is a LAN port, that LAN port can be accessed one person at a time. No two person can access the LAN port at the same time. So mutual exclusion properties hold in the case of LAN port. Similarly for the different, maybe for accumulator, maybe for processor, maybe for some file system, maybe for some register, it can also hold. So for this case, you cannot do anything. What about the hold and wait properties? Must guarantee, the system will guarantee that whenever a process requests a resource and it does not hold any other resource. How can you do that? Require process to request to be allocated all its resources before it begins execution, or allow the processes to request only when the process has none. So somehow we are trying to break that situation that if you want to request some other resource, then the previous resource you must have to release. So you cannot ask for extra resource or any other resource when you have already in hold. If you go for that, then there may be a possibility of starvation. Some of the process may not get chance to get all their required resources. So that's why it can lead to a low resource utilization. But to prevent deadlock, there is one way. So to prevent deadlock, you have to incur low resource utilization or starvation. There can be a possibility of starvation. There can be a possibility of starvation.
Sir, could you explain the starvation part, sir?
What is starvation? Jano?
Yes, sir.
বলো আমি বলেছিলাম যদিও আরেক বলো
Sir, when a process is ready for execution but it's delayed by the operating system.
Why?
So, because some other process is taking a lot of time of the CPU.
Not only CPU, in more abstract term, we can say
Low priority.
the process is not getting its required resources. CPU can be a resource.
Yes, sir.
Okay, so when a process is not getting the required resource and it is being delayed forever, that is called starvation. On the other hand, some other process are getting the resources. So maybe there are 5 processes: P1, P2, P3, P4, P5. In some order, all the processes are getting the resources and they are executed. And somehow process P1 is not getting the resources, the required resources, the way it is looking for. So the execution of P1 is delayed forever. Forever in the means it doesn't know how much time after what time it will get the chance to be executed. So this is called starvation. So if you want that hold and wait characteristics will be failed, to fail the hold and wait characteristics, what mechanism you are taking? You are taking a mechanism. The mechanism is whenever a process requests for a resource while he is holding some resource, it has to ensure that I release my holding resources and then only I will request for my new resource. If you enforce these properties, then it might be a chance that there are some processes like P1 who will never get chance to get all the required resources and will be executed. So that leads to starvation. And that is also called low resource utilization because P1 is not getting all its required resources.
Sir?
Balu.
Sir, but when the process needs to relieve the previous resources to get the new resource, and in the other end it needs all many resources to execute at the same time, then it cannot run, no sir. It
That is
cannot.
starvation. That is starvation. वही तो मैं बोल रहा हूँ. That is starvation. That is starvation. P1 needs certain resources, maybe resource 1 type of some resource of resource 1, some instance of R2, some instance of R3. All these resources are needed by P1 simultaneously, but that is not happening. That is not happening. In that case, P1 will never get chance to be executed. So that is starvation. P1 will wait forever for those resources to get. ठीक है Popuri?
Yes sir.
Okay, so in one way you can prevent the system to come in deadlock. On the other hand, you are incurring starvation situation. No preemption. If a process that is holding some resource and requests another resource, that cannot be immediately allocated. And then all the resources currently being held are released. So whenever, suppose P1, there is an assignment of R1 resource and P1 is requesting for R2. When P1 is requesting for R2, it has to release this resource. And this resource will be preempted because will be released by P1 and it will be added to the main resource list. Such that this can be used by some other process. So whenever a process is holding a resource and requesting for another resource, it has to release the previous resource. It has to release the previous resource, and if it doesn't allow this process to be executed, then it will release all the resource. And all this resource will be added to the main resource list. So this is called preemption. You are preempting a currently running process. Yeah. None of the car can proceed further. None of the car can proceed further. So what you are doing as a driver, you are taking the car back to its previous position. So basically in the language of computer science, what we are saying, this car is releasing its holding resource. This car is releasing the holding resource because car 1, car 2, car 1 was holding this portion of the road. Car 2 is holding this portion of the road. So what car 1 will do? Car 1 will release this portion of the road and will go back to its previous position. This is called preemption. So the system will allow the process to go for preemption. It will release all its existing resources, and that existing resource will be added to the main list such that other required process can use it. Here C2 can use that resource. After some times, process P1 will again start. After some times, car C1 will again start. Hopefully by that time, he may get this portion of the bridge free. Because C2 will not be there, but there is a possibility that other car may also come. Or there may not be a possibility that it will find the bridge is free. So basically, the currently running process is preempted. Currently running process is preempted, and all the existing holding resource are released, and that resource are added to the main list. Okay? After some times, this process will again restart. This process will again restart. The fourth one is circular wait. Impose a total ordering of all resource type and require that each process request resource is an increasing order of enumeration. Maybe you can do some kind of ordering in the processes. Earlier what was happening? The process can be executed in any order, and that may lead to an deadlock situation. So In the next moment, what we can do, we can make a increasing order of enumeration. Maybe by the process ID, in the order of process ID, we arrange the process. The lower the process ID, will get the chance first. And that may lead, maybe, again, there is a possibility. You cannot give a guarantee that that will not lead to deadlock. But there may be a possibility that if you go for that order, that may not lead to a deadlock situation. So instead of sending the processes in haphazard order, we are making an order. What is the order? Is the increasing order of enumeration and sending for execution. So somehow our objective is to not satisfy all the four conditions. If somehow we can ensure that one of the conditions will, or one of the characteristics is not satisfied by the system, then there won't be deadlock. That is the prevention mechanism.
Sir, how can we say if we follow that order, it might?
It might. There is no guarantee that they don't be deadlock. So if you send in haphazard order, there is a deadlock, you find. So in the next moment, what you do, you restart the system. I mean, the system will restart the execution of all the processes and will send in the order of enumeration. In the order of enumeration. Maybe they are following some separate order. And that may not lead to a deadlock situation. You cannot, of course, you cannot give a guarantee because we are trying to prevent somehow. So there is no 100% assurance that it will not be a deadlock. So that's why the most robust mechanism is deadlock avoidance. So deadlock prevention is not a robust mechanism. You are taking some kind of heuristic that cannot give you a guarantee that it will always be a deadlock free situation. But if you go for deadlock avoidance mechanism, then it will ensure you that this will not come to a deadlock situation. What is that? Before the processes are sent for execution, each process will declare the maximum resource requirement. If its resource requirements are fulfilled, then only the process will be sent for execution, otherwise not. So through that their resource requirement, system will try to find out a sequence of processes in which, if they are sent, their resource requirement will be fulfilled. And that sequence is called a safe sequence. That means you have, suppose in a particular moment, you have 10 processes in the system. Each process has a maximum number of required resources. P1 needs this resource. P2 needs this resource. P3 needs this resource. That many number. Then operating system will try to find out a sequence in which if it send the processes for execution, all their resource requirement will be fulfilled. Their resource requirement will be fulfilled. Maybe that order is maybe P3 first, then P2, maybe P1, maybe P4, like this way. Maybe in some other order. If you find this order, then we will say it is a safe sequence. Or safe sequence. You find a safe sequence. And if you find a safe sequence, your system is in safe state. And if there exists a safe state, no deadlock. If you don't find a safe state, that means unsafe state, then there is a possibility of deadlock. And deadlock avoidance will ensure that the system will never come to a deadlock situation. I will take an example, then it will be more clear. Okay, so if the system is in safe state, there is no possibility of deadlock. If it is an unsafe, that means there is no safe state or safe sequence. If there is no safe sequence, then there can be deadlock, there may not be deadlock. Because if it is an unsafe state, the possibility that there won't be a deadlock, but there may be a little bit chance of deadlock. So with this idea, an algorithm is designed. This algorithm is called Banker's algorithm. Okay, once we go through the algorithm, again we will come back to this. Then your idea will be more clear. Can anybody say how the bank operation is done when you go to a bank counter with a bearer check or withdrawal slip to withdraw money from bank? After submitting the check to the bank counter, how this is processed, or what are the steps the teller counter person used to follow? Can anybody say?
Authenticity, checking the authenticity of the account.
First it will check whether the check is an authentic check or not by the check number and the signature.
And then also the account number exists.
Signature, whether it is a correct signature or not. Next,
account number exists in the bank or not.
Okay, so all these things passed. Next,
amount is available or not. The amount.
How does it check?
Amount from the bank account number, the amount will be
I mean, what checking mechanism is being done?
Balance check.
So it checks the amount which you are looking for, or the amount you want to withdraw, and the balance you have in your
bank account.
Okay, so suppose you want to withdraw 10,000. Suppose you want to withdraw 10,000 through check. If you submit that check, first it will check the authentication, then the bank counter person will check the available balance in your account. If the available balance is less than the 10,000, then they will return the check. They will not process it. If the balance is higher than the requested amount, then they will process your check and will hand over the cash in your hand. So before handing the cash to your hand, the bank people will check the amount you are looking for and the balance you have in your account. If they find that the balance in your balance in your account is higher than the amount you are requesting, then they will process further to execute the check. Otherwise not. It never happened that once they deliver the amount to your hand, they try to check. It never happened. First they check it, then they deliver the account fund. Or rather we should say, first they check it, the available balance and the amount you are requesting, and then they process your check. Clear? With the same concept, the banker algorithm works. That's why the term is bank. Whenever a process tries to execute, it will request the maximum amount of resource it is looking for. If the resource requirement is fulfilled, then the process will be sent for execution. Otherwise, it will be kept in holding. It will be kept in waiting state, ready state. It will not be sent to the run state. So before sending a process to run state, it will check its maximum requirement of the resources. Take the example of Banker's algorithm. Suppose there are 5 processes: P0, P1, P2, P3, P4. There are 3 resource A, B, C. This is allocation matrix. What is this? P0 is holding single instance of B resource, no resource of A and no resource of C. P1 is holding 2 resource of A. P2 is holding 3 resource of A, 0 resource of B, 2 resource of C. P3 is holding 2 resource of A, 1 resource of B, 1 resource of C. P4 is holding 0 resource of A, 0 resource of B, and 2 resource of C. This is current allocation. This is called max P0 requires maximum 7 instance of A resource. P0 requires maximum 5 instance of B resource. P0 requires maximum 3 instance of C resource. P1 requires maximum 3 instance of A resource, maximum 2 instance of B resource, 2 instance of C resource. Do you understand the max and allocation matrix?
Yes, sir.
Okay. Now, can you tell me what will be the need matrix? What can be the need matrix? Need means further requirement.
Max minus allocation.
Good, very good, very good, very good. Bolo. So it will be max minus
Allocation.
max minus. So क्या होगा बोलो इसमें value?
Sir, 7.
7 4 3 4 3.
Next.
7 4.
Next.
1 2 2.
1 2 2. 1 2 2. 3 0 0.
6 0 0.
Sorry, 9 6 0 0.
6 6 6 0 0 6 0 0
0 1 1.
0 and 1.
0 1 1 1
Next.
4 3 1. 4 3 1.
4 3 1.
ठीक है? So this is my need matrix. So this is the need matrix for all the processes, and this is my currently available. Now tell me, in this situation, whose requirement is fulfilled out of P0, P1, P2, P3, P4?
Sir, P1 and P3.
P1 and P3. P1 and P3.
P1 and P3. So you can choose any one. Of course, you will go for ordering. So you allow P1 to be executed first. Allow P1 to be executed first. Okay? Once you allow P1 to be executed, definitely after a finite amount of time, P1 will be completed.
Yes, sir.
And once P1 completes, it will release.
Sir, A, B, and C.
All its resources. A, B, and
The
C.
resources occupied by P1.
Yes, sir.
And that will be added where?
Sir, available.
Available.
Good. Very good. That will be added in the available matrix. So what will be the new available after the completion of P1?
So 654.
654.
So 654.
Maximum, sir, maximum should be added or
Max should be added. বলতে পারো Abdul, why? Abdul, can you tell why the max will be added?
So max will be added because that's the maximum number of resources instance it is withholding.
Okay, so max will be, so the new available matrix will be
654.
654. 6, sorry.
654.
6. ठीक है? Now I have 4 process, P0, P2, P3, P4, whose requirement is fulfilled. You start from the beginning.
Sir,
P2, sir.
Sir,
we'll not first subtract max from available when we are allocating those things to the P1. Sir, if we from available we are giving everything to P1 that it needs, then we will have in available 1, 1
Okay,
and
Karo.
0.
Okay.
So in available we have 1, 1, 0, and then we add max 3, 2, 2. So we'll have 5, 5, 2, 2. 5.
বুঝলাম না।
স্যার বলছে যে available থেকে আগে ম্যাক্সটা মাইনাস করবো তো, like when we are giving everything
মাইনাস করবে কেন?
sir, when we are giving everything, like P1 needs more 1, 2, 2.
Oh, sorry. Sorry. নিটটা মুছে ফেললাম গো আমি। নিটটা কেউ লিখেছো দেখো তো?
হ্যাঁ স্যার, 743,
হ্যাঁ
743
743
122
122 600
600
011
011
431.
431.
So this is the situation, right? So available is 3222 and the requirement of P1 is fulfilled. So you can allow
So
P1
then we'll minus 122 from available 332.
Okay. So available minus need.
So then we have available, it will be 210.
210. And what is
So
the
then
allocation
when
of
P1
what is the allocation of what is the allocation of P1 now?
322.
322.
So now we'll give every P1 has finished executing, then we'll return 3222 available 210.
So what will happen?
So 532.
So the new available is 532.
Yes, sir, that was what I was saying.
Okay. So instead of subtracting, you can directly add. Chalo, etai koro. No problem. Okay. So now the new available is 532. Any doubt?
স্যার কি করলেন আরেকবার বলে দিন।
निखिल बोलो। क्या जोर से बोलो।
So first we'll need to see how much P1 needs, so that is 122. So we subtract that from available. Then we have in available we have 210, and P1 is getting all that it needs, so it is 322 now in the allocations field. So now when P1 is finished executing, 322 will return to the available one. So now we add it to the 210, so we get 532 in available.
So the new available is 532.
Sir, how is P1 getting 322? Allocation 322, how that came?
maximum requirement is 322. So 322 will be allocated.
Maximum requirement is 322, so we decided that P1 will execute first. So we gave it everything that it needs. So now it has 322 in allocation.
Sir, but it needs 1 to 2. Right. Then why are we giving?
But we are not
Nikhil,
giving
you are wrong.
P3.
Nikhil, you are wrong. See, P1 का मैक्सिमम रिक्वायरमेंट है 322, ऑलरेडी एलोकेटेड है 200. उसका फर्दर जरूरत क्या है
1 to 2.
1 to 2. So you are subtracting 1 to 2 from available.
Yes, sir.
And giving it to
So P1.
P1. So नया P1 का एलोकेशन कितना है
3 to 2.
3 to 2.
3-2.
1 to
नया
2.
अवेलेबल क्या है
210.
210.
So once P1 is completed, what will happen?
3 to 2 will add 3 to 2 to 210.
बोलो क्या कहाँ where is the problem? Where is the problem? बोलो अब्दुल सप्तऋषि.
Yes, sir. I
Sir,
agree with this.
Do you agree this?
Yes, sir.
Yes, sir.
किसका कोई डाउट है Anybody has any doubt with this? बोलो ना किसी भी ना. So I assume that you don't have any doubt. So P1 is completed. Okay. There is no more requirement of this need. Now I have P0, P2, P3, P4. Whose requirement is fulfilled with this?
P3 and P3.
So P3.
P3, P4.
P3 or P4. So you allow P3 to be executed. So P1 का बाद P3. P3 का allocation already 211 है. उसका फर्दर क्या चाहिए 011. So subtract this from here.
521.
521. Add it here.
754.
222.
743
স্যার বড় 746 কি বলে যাচ্ছে
তো 743 হবে না স্যার ও
আরে
222
P3 তে কত হবে
ও স্যার ওখানে তো 222
222. So P3 will be completed in finite time and
Yes,
that
sir.
will be added here. So the new available is
743
743.
So 743.
743.
Sorry, 743.
743 and the P3 is no more existence. What is my new requirement? I have
P0 is.
Sir, anyone we can execute. First, P0 will execute.
P0. So allow P0 to be executed.
P0.
Do the same operation. Available is
Available 000.
available is
Available.
743 and the requirement is 743.
Yes, sir.
Okay.
000.
Add this 743 to 010.
753.
753.
So the new available is
753.
So this available.
753. So,
753. Where is the confusion? Next, so P0 is completed. Next you have P4. So the requirement of P4 is also fulfilled.
next sir P2 तो करा जाए.
Sir, next to P2, sir.
P2 करो चलो P2 करो. Okay, P2 is there. Next you allow P2 and then P4.
Then P4. Yes.
So you have to show every step. I have a very small this pad, that's why I cannot show you the entire board work. You have to show each step. So this state, there can be several such shape state. This is called shape sequence. This is called shape sequence. If you find a shape sequence, then we will call it is a shape state. The system has a shape state. And if the system has a shape state, then there won't be a deadlock. This is called Banker's algorithm. Before processing the check, the teller counter person will verify the amount you are looking for and the available balance you have. If the available balance is higher than the check amount, then the check will be processed. So in the same way, available and the requirement. This is available, need or requirement. Requirement will be checked with the available. If the requirement is less than or equal to with the available, then it will be processed. Otherwise not. That's why the name of the algorithm is called Banker's algorithm. So you may get several step sequence. For example, P1, P3, P0, P4, P2, you may get another step sequence. Ultimately, you have to get the step sequence. If there exists a step sequence, then it is called the system has a safe state. Otherwise, there is a possibility of deadlock. Bolo, is the example clear?
Sir, one question, sir.
Bolo.
স্যার এখানে যদি প্রিএমশন হয় তো লাইক পুরো সিকোয়েন্সটা তো হয়ে যাবে।
এখানে প্রিএমশনের ব্যাপারই আসছে না তো।
না মানে লাইক if you are doing in a multi processing environment তো লাইক প্রিএমশন হবে কি লাইক will prevent that?
বুঝলাম না কথাটা।
মানে লাইক
if you go for deadlock avoidance, there is no questions of preemption. You will send the processes on the basis of requirement and availability. Preemption is coming only when you are talking about the deadlock prevention, not in deadlock avoidance. This is deadlock avoidance. Deadlock avoidance. This is deadlock avoidance. This is deadlock prevention. In deadlock prevention, we discuss no preemption. Somehow you have to manage that. We can preempt the process. And
so basically these two are different ways of handling deadlock, right?
Yes, correct. These are the two different ways of handling deadlock. One is deadlock prevention, another is deadlock avoidance. In deadlock avoidance, you are finding some mechanism to find out a safe sequence on which if you send those processes, they will never come to a deadlock.
Okay, sir.
Okay. So you are trying to find out a sequence among the processes. You are trying to find out a sequence among the processes in which if you send the processes, they will never come to deadlock situation. And to find that safe sequence, you use this algorithm called Banker's algorithm. Banker's algorithm. Whatever we discuss, the same thing is written here. You have an available, you have a max matrix, you have an allocation matrix, you have a need matrix. How do you get the need matrix?
Max minus allocation.
Max minus allocation. The same thing is written here. Then how do we process? We are processing, we are checking from the need and the request. And need, need and the available. Whose requirement is fulfilled, allow the process and finish it. So delete it from the list. From the remaining processes from the list, again you check whose requirement is fulfilled. जिसका fulfill हो रहा है, allow that process to execute. Once the execution is complete, delete this process from the list and add the allocated resource to the main list. So every time you are in every iteration, you are deleting one process and allocating the holding resource to the main resource list, the available one. And that's it.
Sir?
Bolo.
Sir, for a particular process, is it always possible to determine all the resources that it requires prior to its execution?
That is the assumption of this algorithm. If you have to follow this algorithm, then there is no other way, because that is the assumption of this algorithm, that at the beginning or in the priority.
Because during the execution,
just see this one. Just see this one. Each process must a priori claim of maximum use. Practically, it may not be possible always. You are right. Practically, it may not be always possible that each process will declare its maximum requirement at the beginning. In that case, you can go for prevention. So most of the operating system, even Unix, what does it do? It pretends that there is no deadlock in my system. You allow the processes to be executed. अगर deadlock होगा तो हम लोग देख लेंगे बाद में. So the option is, even we pretend that there is no deadlock in my system. If it comes to a deadlock situation, we will restart the system. We will not take care from the beginning. अगर होता है, then we will take care.
Is Banker's algorithm used in Unix or not?
In normal operating system with which we are familiar, there is no operating system that uses Banker's algorithm. It's a theoretical aspect. Maybe some specialized algorithm they may use, but normally whatever operating system that we use, like Windows or Linux operating system, they doesn't use Banker's algorithm. It's a theoretical aspect of it. It's an algorithmic aspect. But practically, they pretend, because the moment you go for Banker's algorithm, the possibility of resource utilization will be less. Resource utilization कम हो जाएगा, क्योंकि you are degrading or you are decreasing the parallel executions. You are going for serial execution. Instead of going for parallel execution, you are making a serial execution. See, you are making a serial executions. You are forcibly running the system serially.
Yes, sir.
So there is a trade-off. I mean, the moment you go for, hey, actually one of your senior is calling passed out senior. So okay, for this, ঠিক আছে, deadlock টা আমার মনে হয় হয়ে গেছে. So if you have confusion, you please let me know. ঠিক আছে?
Okay.
Okay, sir.
ঠিক আছে? Still, I mean, I will be there. If you have any questions regarding this, you please let me know. My email, WhatsApp, everything is there with you. Please let me know. Okay. ঠিক আছে?
Okay, sir.
Okay, sir. Thank you, sir.
Okay.
Thank you,
Thank
sir.
you, sir.
Thank you. Bye.
Thank you, sir.
Thank you, sir.